So, hello. Today we're joined by Dr. Martin Weidman. He is the Gellert Family Professor of Food Safety at Cornell University. Martin received a veterinary degree and a doctorate in veterinary medicine from Ludwig Maximilians University in Munich and a PhD in food science from Cornell. His research interests focus on farm-to-table microbial food quality and food safety, and the application of molecular tools and quantitative and modeling approaches to study the transmission of foodborne pathogens and spoilage organisms. His team has published over 500 peer-reviewed publications, which have been cited over 40,000 times. He and his team are regularly asked to help industry across the world with a range of microbial food safety and quality challenges. He is a fellow of the American Association for the Advancement of Science, the Institute of Food Technologists, the American Academy of Microbiology, and the International Academy of Food Science and Technology. So thank you for joining us today, Dr. Weidman, and we're excited to learn more about log reduction and how to demystify it.
Thank you. It's my pleasure to be here today. So what I'm going to talk about is log reduction, how it's used, how it's abused, and how to appropriately use it in produce safety and beyond. I started out with a little warning. With the time allotted to me, I'm going to make some simplifying points that, some of you are deep into math, and the math of log might cause you some stress and heartache. But I think it's important to do this to really make the point and drive the point home. So let's start out with an outline. And I'm going to start out with how are we using the term log in food microbiology and produce safety, and why do we use this term? So here's some expressions one made here around log. So you may have heard things such as this produce wash process provides a 2 log reduction. E. coli shows less than 1 log growth on onions stored at 10 degrees C for 30 days, so it doesn't really grow. Or we inoculated product at 6 log CFU per gram when we did an experiment, and everyone's like, why so high? Why are you starting with those higher numbers? Now, all of these have slightly different applications of the term log. So what is log? Let's start with that. Be very simple. 10 is the same as 10 to the 1, which is 1 log. So when I'm talking about 1 log of organisms, I'm talking about 10 organisms. Following up on this, 100 is 10 to the 2 is 2 logs, 1,000 is 10 to the 3 is 3 logs. Or if we go the other way around, 3 logs is 1,000, 6 logs is 1,000,000, and 9 log is, but you pause to sort of think about it, 1 billion, right? And then 12 logs would be 1 trillion, and so on and so on. So why? Why are we using log? It's really traditionally used for statistical reasons, because these log transformations, so when we take data where we have 100 and call it 2, because we transform it into a log, makes the data more normal. And if you remember back to some of our statistics classes, that bell curve, that normal curve, is what everyone wants when you want to use your data to do some statistics. It means the data are less skewed, and it makes some statistical analysis that require a log distribution or a normal distribution easier to be analyzed. Log transformation can also be easier for visualizing data patterns, and it reduces variance. The variability is less extreme, and the variability of the data point is more consistent, again, helping with some of the statistical analyses. However, it also makes data and things a lot more confusing. So what we see here is on the top, we see a graph that shows the income of a number of different people. And you can see it starts at 0 and goes to about 600,000. And you can see that most of the people have an income that's probably around 50,000. And very few people have higher incomes, particularly above 200,000. But that's not a normal distribution. Now, if we take this and log transform it, we see this nice, more normal looking distribution. But also, you have data that most people won't understand. If I tell you, hey, what's your salary, my friend? And I say 5 logs, no one will know what you're talking about. And that is one of the issues with log transformation. When we use it, often it makes the data difficult to understand and difficult to follow, as is illustrated more on this slide when we zoom in on that log transform data. So useful for some mathematical and statistical purposes, sometimes challenging for interpretation and use. Now, if you don't have to take my word for this, there are a number of people who have written about why microbial growth data require transformation, such as this paper. And, it gives you a more realistic example. If you look at microdistributions, for example, growth rate by temperature, we look at the distribution, and if we log transform these data, we get lower variance at these growth rates. So what are some of the specific uses of log in food microbiology? And I'm going to also translate those for you. So I talked about this produce wash process provides a 2-log reduction. That really says this produce wash or this process gives me a 100-fold reduction of a specific bacteria. So we have two issues with this statement. A lot of people won't really easily know what 2-log reduction is, that it's a 100-fold reduction. The second is that we sort of assume it's a universal 2-log reduction. When we talk about a log reduction with regard to bacteria, we typically talk about a specific group of bacteria or a specific group of organisms, such as Salmonella, E. coli, or Listeria. The term E. coli shows less than 1 grows. That means less than 1 log grows. This means it shows less than a 10-fold increase in numbers if we store onions at a certain temperature or something else at a certain temperature. The paradigm's always been in 1 log or less increase in numbers really is so small and relatively within variability that it's not a big deal. However, on the scale where we do produce processing and distribution, it can matter. And when we say we inoculate a product at 6 log CFU per gram, means we inoculated with 1 million bacteria per gram. Probably the easiest ones to translate. So what's the problem with log? Why do we even have to talk about it? And I'm going to give you some, different problems and challenges. Problem number one is, you already alluded to that a little bit, is people don't think in terms of logs. Think about, people think about money. It's always a comparison. It's numbers, just like bacterial numbers. If you were to go to bed at night and you were a little kid and you have $6 in your piggy bank, shown on the top right, and you wake up and you have $5, you're probably not going to lose a lot of sleep the next night over that. It's a change, but it's a relatively small change. And so we're used to it. Change from 6 to 5, not a big deal. However, when we talk about log scale, if you were to go to bed with 6 log in your mutual fund now that you're an adult, and you wake up with 5 logs in your mutual fund or your investments, that is a big deal because you went from 1 million to 100,000, 10-fold reduction. So if you just use log numbers in conversations, for example, with staff in produce facilities, as we talk about some of these microbial control strategies, they may not understand the scope and the scale of this because of these log reduction values. That means people may not pay enough attention to small differences, might not even think that 1 log versus 2 log is a big deal because they're thinking $1 versus $2. When we're really talking about 10 versus 100. And therefore, treatment, microbial reduction process that gives you a 2-log reduction is substantially better than one that gives you a 1-log reduction, 10-fold better. You're not talking about a 1 to 2 difference. So first thing is a communication and a comprehension issue sometimes when we refer to logs. Second problem is logs are used in different contexts. We talked about log reduction, but then we talked about absolute numbers, okay? Those are different concepts because absolute numbers we look at differently than reductions, and I get into that a little bit more about the next slides. We also sometimes use log for growth rates, how fast the organism is growing. Challenge there is we have different types of log. We have a log to the base 10, we have a natural log. Some of these growth rates typically should be expressed in natural log. Often people don't keep track of that, which can give us challenges when we look at databases such as Combase, where people sometimes may not have reported the correct units. So with the common use of log and different types of log, including natural logs, we have problems interpreting the data and problems sometimes even understanding what exactly people are talking about. Third problem is that math with logs is very easy to do wrong. And it goes back to the misconception. typically, and I've seen this multiple times, if you have 2 logs of something and 2 logs of something else, people say, well, 2 and 2 is 4. But with logs, it isn't. For example, if I were to inoculate a product with 2 logs of Salmonella Newport and 2 logs of another Salmonella, how many Salmonella do I have? I don't have 4 logs. I actually have 200, which is 2.3 logs. So 2.2 logs of microbes is really 100 plus 100 equals 200. So when people do math with logs, very often errors sneak in that might be very difficult to detect. However, while you can't add absolute log numbers, you can add log reductions, which just gets very confusing. If I have a 2-stage produce wash, where I have a 2-log reduction in stage 1 and a 2-log reduction in stage 2, that gives you a 4-log reduction, so a 10,000-fold reduction. So when we talk about reductions, we can add logs. When we talk about absolute numbers, we cannot. It will give us incorrect numbers. To illustrate that, so if you have a 2-step process, and here we take 1 log reduction. So we start with 100 cells. We have a 1 log, so a 10-fold reduction. I have 10 cells that are surviving. If I do another 1 log reduction, another 10-fold reduction, I end up with 1 cell, which is a 100-fold reduction from the beginning. So making sure these math are done correctly and realizing 2 log reduction processes are substantial, or even a process that assures a log lower than normal in a field, plus a process that gives us a 2-log reduction in a wash, still gives us a total of 3-fold reduction of overall risk and overall contamination level potentially. So conclusions of that part is you have to be cautious when people do math with logs. Check the math, make sure the correct concepts and findings are represented. Be cautious when someone gives you log math. When in doubt, do what I call a common sense fact check. Take the log data, retransform it in real numbers, and then check what these numbers tell you when you add them or when you multiply them. Don't trust your numerical intuition with logs and realize that other people might rely on their numerical intuition. And you think, oh, that looks like a small difference. With log, that might not be a small difference. It might be a substantial difference. When you look at a graph saying, wow, these error bars or whatever, they look pretty small. It's not a very variable process. The values are log transformed. There might be substantial variability, which might impact some of your decision making, might impact the reliability of a reduction process that you use, such as a produce wash or a heat treatment or whatever it may be. And these things, again, not just stuff I came up with. There are people who talk about the challenge with log transformation when we try to estimate measurement uncertainty. And it brings up this issue that microbiology, typically bacterial counts are log transformed. However, when we look at standard deviations, when we look at uncertainty, what we get with log transformed data is often meaningless, or maybe safer to say, at least can be very misleading. So you have to be very careful about these standard errors and these error bars you see. And it's even so far that some people recommended don't log transform count data. So this is not a universal rule that all data have to be log transformed. Quite the opposite. Sometimes a log transformation might be helpful, sometimes it might not be. So let's talk about interpretation and misinterpretation as we practically use log data in industry and to make food safety decisions. So back to some of the examples I mentioned. So some of the sort of paradigms that people may often hear is if bacterial numbers increase by less than 1 log, there's no real growth. Sometimes we've told any good critical control point needs to achieve at least a 5 log reduction to effectively control a risk. And anything less than 1 log difference is just noise and is expected. None of those are really true. They're very simplifying generalization that have been around for a long time, but where we are today in the sophistication of food safety, carrying these simplifying sort of assumptions and interpretation over prevents us to really effectively manage food safety risks, which is what I'm going to outline a little bit more in the next few slides. So let's start with number 1. If it's not 5 log reduction, it's not good enough. It's not a real risk reduction. We cannot look at this so-called 5 log reduction in isolation. So let's first talk about what a 5-log reduction is. It's a 100,000-fold reduction. So what that means, if I were to start with 100,000 bacteria per gram, apply a 5-log reduction process, I end up with 1 bacterium after a 5-log reduction. But I will get the same final number if I think of the 1 bacterium per gram as my final product if I start with 10,000 bacteria and have a 4-log reduction. Or if I start with 1,000 bacteria and have a 3-log reduction. So I can achieve the same margin of safety for my final product with different log reductions, depending on what my load, the bacterial levels are that come in at the beginning. And this is very, very important and has been practically used because to design processes and use processes that give us less than this magical 5-log reduction, which, by the way, is really based on a paper that's more than 70 years old when we started to redefine the temperatures for milk pasteurization. So why does this matter for produce safety in particular? You can create a fairly safe product with less than a magical 5-log reduction. There seems to be a hesitancy in the produce industry to call wash waters, wash treatments a kill step. But there's nothing that says 5-log reduction is kill and 2-log reduction might not be. It is a question of definition. You can design a system where you do stringent testing in the field to assure your raw material comes in with a low microbial load and specifically with a low load of the pathogens of concern, which typically will be E. coli and Salmonella, and then add a log reduction process on top of that, which could be 2-log, could be 1.5 log, could be 2.5 logs, to give you few enough remaining organism pathogens to minimize food safety and business risk to what we consider an acceptable risk. If you think about current applications of the 5-log reduction in dairy, dairy doesn't test raw milk for pathogens. They assume they're there. And therefore, based on historical data, they might need a 5-log reduction to get an acceptable margin of safety. However, if you're sure that your raw material is a low level through testing and other procedures such as GAPS, then a substantially lower reduction than this infamous 5-log reduction can still give you a sufficiently safe product and help you to effectively manage food safety and business risks. And this, again, is not something I came up with. There have been papers that looked at the risk of salmonellosis from consumption of almonds, which exactly did this. They looked at the mean concentration in the raw material, assuming different mean concentrations, 500 MPN, so 500 salmonella cells per 100 grams, 200, 120, 50, and 20. They looked at total amount of almonds consumed. They looked at what a treatment, and the treatment there was defined as a 4-log reduction, would give you in terms of salmonellosis cases. And I would say if you can keep your numbers low enough, less than 20 per 100 gram, and you're selling 30,000 kilograms or 30 tons of almonds are consumed, you get less than 1 case per consumption, while untreated gives you 5,000. And most people would agree that that is a sufficiently low risk. So almond industry did it. They showed that 4-log reduction is sufficient to get a reasonably safe product. But even 4-log reduction, there's nothing magic about that. More testing, lower initial levels, a 3 or 2-log reduction might give you sufficient reduction of risks. Misconception number 2, 5-log reduction will always give you a safe product. Yes, you might be okay with a 2-log reduction, but 5-log reduction is always safe. Not the case. Do another little math exercise. So 5-log, again, reduction is 100,000-fold reduction. You have 1 salmonella per gram. If you think of per gram, which is a very small amount, no one really just consumes a gram of almost anything except maybe spices, you will end up with 0.0001 salmonella per gram after a 5-log reduction. And we can probably all agree that that's very, very small and that we might even be willing to call this. There are no salmonella. Now, if we look at a scale that's much more reasonable for commercial production of almost anything, let's just look at a 100-kilogram log. If I have 100 kilograms of a product, where I still start with 1 per gram, but now the 1 per gram is the same as 100,000 salmonella per 100 kilograms. Now I'm applying a 5 log reduction to 100,000. I'm left with 1 salmonella per 100 kilograms. Clearly not nothing. It's low, 1 per 100 kilograms. It's so low that most finished product tests will not detect it, but not low enough that you will not get human illness cases. Not low enough for it not to be a human disease risk. If you take this even larger to a larger lot size, let's say a lot of 1 ton, which is 1,000 kilograms, now we have 10 salmonella per lot. And that starts to go to a point where you might have one person get sick with just 1 ton. Now, if you look at a lot of commercial productions, we look at lot sizes or productions much, much larger than 1 ton in many cases. So 5 log will not give us sufficient reduction, particularly if our raw material might have reasonably high levels, and 1 salmonella per gram is actually pretty high. Okay. Most tests, where we test 1,500 grams or so in our field, for example, would give us reasonable assurance that we have levels much lower than that. Second challenge that is related is there's often a focus on log reduction without considering the variability. And that means another reason why 5 log reduction doesn't always give us a safe product. And I'm going to give you sort of a common sense example of that. Let's say you have a kid and you need to decide which of your friends this kid or their friends your kid drives home with tonight. And you have the driver records of 2 of their friends, driver A and driver B. And we know that driver A drives an average of 55 miles per hour in a 55-mile zone. Seems like a very law-abiding person. And driver B is a little bit more like me, drives about 10 miles faster than they should be. Which is the safer driver? Which of these drivers would you pick for your child? Most people will show little hesitation to say driver A. However, they made a classic rookie mistake. They did not look at variability. What if the average of 55 miles per hour came upon because this is the average of 3 drives that we kept track of, and once that person drove 15 miles an hour, once they drove 55, but once they drove 95 miles an hour, 40 miles faster, while the other person is a very consistent driver, 64, 65, 66 miles an hour. With that information, which of the 2 drivers do you want your kid to drive with? And that's, most of us will probably pick driver B. Yes, driver B on average drives too fast, but the real risk is not with 65 in a 55-mile zone or even 66 in a 55-mile zone. The real risk is when someone drives super fast. And one could even argue there's also risk when someone drives super slow. So we need to consider the variability, not just look at the means or the averages or the medians, whatever we measure. Most people forget about that. Now that does apply to produce safety and food safety in general. Give you 2 examples of 2 processes, process A and process B, and you can see that they have similar means. However, process A has a lot more variability than process B. Obviously, you want to pick process B because that means you have a very low chance that every now and then you get a low level of reduction, in this case, less than 4 log reduction. It's a highly variable process like here. You have a 10% chance that you have less than 4 log reduction, which obviously those are these rare moments where you increase your risk. Here it's a 1 in 10 chance, here it's a 1 in 100 chance. And it gets more tricky. Now, if you shift some of this distribution and move to process B and C, B is the same, but C now has a higher mean log reduction. Let's say 5.5, so that mean here is further to the right than here. So just looking at log reduction, this looks like the better process. However, due to the high variability, it still has a higher chance of having a day where you get low reduction than this less variable process. So when you think about log reductions, don't just ask about the mean, ask about the standard deviation, ask about how variable a process is in order to pick the process that's at best for reproducibly and reliably managing a given risk. People often forget about that. Clearly, there are many details when we think about how does log reduction relate to microbial food safety risk. Often it's not easy to just do that by back of the envelope math or just looking at data. It is possible to do fairly simple risk assessments to capture these various details. What load of pathogen do you get in? What's your reduction? What's the variability in your reduction to determine which tool provides sufficient risk management, again, whether it's from a business perspective or a public health perspective. So these numbers can help, but as we said from the beginning, don't always just rely on your common sense because it may often lead you astray unless you dig in a little bit deeper. But this doesn't have to be a 1 year, $100,000 process. Some of these risk assessments are pretty straightforward to do. You just need to demand it from the people you work with. And the challenge with this, however, and we got to be important about that, is that none of your processes will give you zero risk. And that's what we call the concept of residual risk, right? We can do whatever we want to for risk reduction. We can use a 7-log reduction with low incoming load. We will still have some remaining risk. But we can also have a low incoming load of pathogens in a 2-log reduction and get a reasonable risk management where we have a residual risk that we might deem acceptable from a public health perspective because it's a product that provides health benefits and from a business perspective. So misconception number 3, that log reduction is an absolute. You talk about this process is a 5-log reduction. But 5-log reduction of what? 5-log reduction of a pathogen like Listeria monocytogenes in milk or E. coli or Salmonella in produce does not translate in an equivalent reduction of total bacterial counts, as we measure it by different things such as aerobic plate count, total plate count, standard plate counts. All microbial methods to give us an idea of the majority of microbes there. It doesn't really count all microbes, but the majority. And that is because these total microbial populations may include organisms that are actually pretty resistant to whatever process gives us that log reduction, let's say heat treatment or chemical treatment. Some spore formers, microbes that form these extremely resistant forms, might survive better than a Listeria and E. coli. Some organisms that are very resistant to heat might survive better. Even in a process such as milk pasteurization, sort of the standard form, what we call this 5-log kill, 5-log heat treatment, is even though we know very well that we get more than 5-log reduction of the pathogens of concern, of your Listeria, of your tuberculosis, of your Salmonella, if we look at the reduction in standard plate count, we typically only see a 2-log reduction. Your milk might start with 10,000 and ends up with 100. Now, most people say, wow, this process isn't working. It's advertised as 5-log. It's not. It's working with regard to pathogens, but you cannot expect the same log reduction in total bacterial counts. You need to rely on the validation of your process with pathogens or possibly surrogates. You cannot substitute total microbes for your target pathogen. So you might often look at some of your processes and say, well, we get a very limited reduction in total bacterial counts. You might still get a substantial and a sufficient reduction of your pathogens of concerns to effectively manage your risks. The other misconception, if we show less than a log increase, means organisms aren't growing. Don't ignore minimal growth. It can still increase food safety risks. That's important when we look at temperatures and other parameters we use to control microbial growth. 0.9 log growth really isn't statistically different than a 1.1 log growth. And with enough variability, it might still give you sometimes where you don't have a 0.9 log growth because it's the mean, but you could get 100-fold growth. So sometimes because of a wide variability in growth parameters. And again, risk assessments are the answer to it. Look at all your parameters together. Low load, a reasonable reduction process, could be 2 log, could be 3 log, could be 1.5 log. Stringent control of growth throughout distribution might give you a better risk reduction than a 5-log reduction without control in the raw material and without stringent temperature control to prevent growth. You need to put it all together in a risk assessment to develop a system rather than focusing one number without variability for one process. Now, math with logs is not just a problem with microbial numbers. Another challenge in many areas of food safety and microbiology is pH. Why? Because pH is also in a log scale. So some of the same problems we discussed for microbial numbers also apply to pH values. pH just is even more complicated. So how so? We talked about log. So 10 to the 1 is 10. 10 to the 0 is 1. 10 to the minus 1 is 0.1. 10 to the minus 2 is 0.001 and is known as minus 2 log. 10 to the minus 1 is minus 1 log. 10 to the minus 3 is minus 3 log. pH is actually on a negative log scale. So pH 5 has 10 times more protons, H plus, than pH 6. So 10 to the minus 5 molar versus 10 to the minus 6 molar. Why is that important? Same problem as with bacterial numbers. We have small differences and people might think they're irrelevant. pH 5.3, 5.7, $5.30, $5.70. Not a big difference in absolute numbers. In pH, these are pretty different in terms of the number of protons there. Many people don't realize that and may not control their pH stringently enough in order to control pathogen growth or pathogen die-off, including in produce washes where efficacy can be highly impacted by pH. So again, that whole system applies, and that challenge of pH, misleading people into thinking these are only small differences also applies to pH. Such a critical parameter in many ways where we control food safety issues. So what are the practical take-homes from this? Log reduction, use, abuse, and how do we demystify it? Use, it makes data prettier and allows for certain data analysis. Yeah, I'm not saying we shouldn't log transform, but I also think we should carefully think about and reevaluate whether we always need log transformation. Abuse is when we take log, particular problem if we take log data and take it as an absolute. I gave you the example of a 5 log reduction. We need to look at variability and many other dimensions of risk and need to look at a system. We can demystify some of log by transforming it back to the real numbers and say, okay, what's a 2 log reduction really? What's an inoculation with 3 log? If I have 2 processes, one gives me a 1 log reduction, the other one gives me a 2 log reduction, how much reduction risk do I really have? This demystification is actually, in some cases, can be pretty easy. Your iPhone, probably your other smartphones can help you with it. You often have something called a scientific calculator, where you have a function that's like 10 to the x here. And I can type in, if I have 2.2 logs, I type 10 to the 2.2, and it tells me 2.2 logs is 158. So if I have a 2.2 log reduction, I get 160-fold this rounding reduction. If that's too complicated for you, you can just type it in ChatGPT. What is a 2.2 log reduction fold reduction? About 158, so about 160-fold. There's easy ways to do these sanity checks to make sure we at least are in the ballpark with regard to understanding what these numbers mean and doing some of these calculations. And I still have to do it sometimes. Sometimes it gets confusing when people throw around log values. I often go back to these sanity checks by just retransforming data to real numbers, saying, what does this really mean? So take-home messages, logs are weird. They are sometimes difficult to deal with. They make differences look smaller than they are, okay? 1 log difference doesn't sound like much. It's a 10-fold difference. We talked about these numbers. Be careful when people throw around log values. Real decision-making needs more than a log reduction value. 5 log good, 4 log not enough, way too simplistic. You need to consider variability, you need to consider initial levels, many other different details such as the pH, what organisms does this log value to relate, to really assess whether a given process for pathogen control is sufficient for your uses or not. Do not fall in the trap of thinking 5 log is the only thing. A 5 log reduction is the only thing that allows you to make and provide substantial increased food safety. You can manage a food safety system very well with substantially lower log reduction values, as the almond industry has shown. But in many cases, you have to get some level of risk assessment to really put it all together to help you understand how much of an actual risk reduction do you get with a system that incorporates all these different pieces. Thank you very much, and I hope this was useful.